We are live, just double checking the feed to see how we're going. I think we're all good, but take a few moments to check before we get online. Are we good? Just checking. Yeah, I think we're all right. All right, so for in this session, what I'm going to be looking at is preparing my Rscript for publication. Things are getting pretty close. Paper's coming along very nicely. This is a paper looking at how we can actually create synthetic datasets from original datasets, which means that we can actually share them, reproduce them, and do some exploratory analysis. Here is a tentative title. I'm not sure if I'm going to stick with this one, but for now, I like it. And abstract's done, more or less. Introduction is pretty much done. And here is the method, and the method is explaining how I actually created the synthetic datasets using two examples. So this walks through how you do it, but of course I'm going to have an associated Rscript so people can actually follow it, and that is what I'm going to be working on today. I do have an Rscript, but it is super messy, and it's basically reflects all the things that I've been trying to do, some that have worked and some that haven't. So what I'm doing here is cleaning it up. Firstly, to make sure I can actually reproduce the whole thing. Sometimes when you're working with scripts, there are some dependencies that you forget. So when people who are trying to do this on a different computer, they can't actually run it. So starting with a fresh and a clean global environment, which is all of the files here, seeing if I can do it. And I've come across a really cool little function here, which actually firstly checks whether you have particular packages that you need. If you do, then they load them. But if you don't, it downloads the packages and then loads them. So this is really cool. And here is the link here. All right, so so far, I think we're only going to need 3 packages. The synthpot package to actually use the synthesized datasets. The tidyverse, which has a whole bunch of different packages to. I'm just going to check one thing. Yeah, which does a whole bunch of different packages for when it comes to how we're actually dealing with the data, and cowplot, which is something I'm going to be looking at today. Firstly, it makes your plots look a lot nicer, but secondly, there are some really handy functions for arranging your plots if you're putting more than one plot together. Okay, for our particular script here, importantly, we're going to set a seed so that the data synthesis can actually reproduce. And I'm trying to comment as much as possible. I remember what it was like when I was learning R, finding how difficult it was to follow what people were doing. And particularly, you'd see a line and you'd think, what the heck are they doing here? So as much as possible, I'm trying to actually explain everything that I'm doing. So here, I'm specifying the seed, and then here I'm actually labeling that this section is looking at the first example here. Let's switch across to Word, which is oxytocin and self-reported spirituality. All right, let's go back here. So we read the data set in, and I'm going to post the data set, which is already public, but I'm going to post it within the Open Science Framework project that I'm going to eventually do. And then what I'm doing here is I'm renaming some of the variables just to make things a little bit easier. They're a little bit longer, but that's fine because there's always copy and paste. But it's a little bit easier to actually figure out what the variables mean. Here is the line for doing data synthesis, remembering that we're specifying the seed that we specified up here. And okay, so this is the data synthesis. Here are the comparison plots. So this creates an object which is ot_com, and what it does is the object has a number of things within the object. So what we need to do is we need to actually extract, and one thing that it automatically does is it creates plots for you. Here I've specified a comparison plot which compares the marginal distributions between the synthetic and the original data sets. Here I've specified 4 variables because these are our 4 variables of interest. We're going to zoom in a bit. here, as before, we can see the distributions or the counts between the observed and the synthetic data sets are very similar. Importantly, there are no big outliers. Now, there are two things which can threaten discoverability or threaten the privacy of potential participants. Now, because synthetic data sets are creating records which don't exist, these aren't real people, it's almost impossible to disclose who these people are. But there are two conditions. There are two conditions in which this may not be the case. The first one is if there are any specific outliers. So if there are any specific outliers, say there was a sensitive population and you knew there was one person in the town that happened to be 90, and then if you look at the synthetic data set and then you see that there's one person who is 90, even though that particular individual is fake, because it's synthesized a value which is close to 90, and there's only one, it's going to synthesize another person which is close to 1. So you're going to know that's the person. So you have to check for outliers, single outliers that is, or outliers where there's only 1 or 2 people. The second thing you want to do is you want to check that there are no, if you have a few variables and a few potential outcomes for the variables, say you're dealing with a range of ages or binary outcomes, it is possible for the data synthesis to actually synthesize the exact same values. So what you need to do is you need to check whether there's any replicates. If you've checked those replicates and checked there's no outliers, then you're pretty much assured that there is no risk of disclosing who the real individuals are. Of course, we can't anticipate what future technology is going to do, but for now, at least we know for now, that these people can't be disclosed. So here we can see that there are no big outliers, or no outliers where there's fewer than, say, 5 people for these categories here. Sorry, fewer than like 2 people for these categories here. The compare function creates an object, and within the object we have to extract plots, which is what we're doing here. I'm going to call it figure 1a, because if we look back at our manuscript, we're saying that the comparison of the 4 main variables revealed similar distributions between the original data sets and no individual extreme values. And the next thing we're doing here is doing, it's one thing to actually look at the counts between the observed and synthetic data sets, but it's another thing to actually look at the relationships between variables. In theory, synthetic data sets should actually retain the relationships between specific variables. So what I'm doing is I've actually created a bivariate comparison between 2 of the important variables, which is self-reported spirituality. Oh, yeah, that's figure 1c. Okay, between self-reported spirituality and age. So let's specify this as that's 1a, which is the main plot. So what I've done here is I've extracted the synthetic data set. So running this function here creates a synthesis, but within that there's a few different bits of the object. So I've extracted the actual data, which is what we're really interested in. And then what I've done is I've added a column to the original data set and the synthetic data set. Let's have a look. So I've added a column which is called data, and then these are all, this basically tells me that all these figures are from the original data set, observed, 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 observed. And I've done exactly the same thing for the synthetic data set, which is here. Here's the data row. What have I done? Synthetic, yeah, there we go. All the synthetic ones. And then I've stacked them on top of each other by using the bind rows function to create merge dat. So we can see that the top is all the observed and the bottom is all the synthetic. So these are our 2 data sets that are put together. Then what I've done is I've created a plot or a scatter plot to compare these 2 things. This is called pmain, this object here. So far, so good. This looks interesting. So what this is plotted is the observed and the synthetic. I've added a bit of alpha because there's a lot of there's a lot of crossover, but you can see that the patterns here are basically the same. So the relationship between these two things across both this observed and the synthetic data sets are extremely similar, and I've put a regression line here so you can see how close these two things are. And that's great, but I think what's really interesting is looking at the marginal distribution. So what you can do is you can actually plot the marginal distributions for both the y-axis and the x-axis, but first we have to actually make the marginal densities. So this little bit here creates for the x-axis, which is looking at age. Let's see if it plots this. It's taken its time. That's all right. Let us try again. Something's happened. There we go. All right, so there's our x-axis distribution, which on its own looks a bit weird. We're going to create our y-axis distribution and flip it because it's going to go on the side, which is the chord flip command there. There we go. That's on the side. And now I'm going to add them all together. I'm going to create this beauty. At least I hope so. Come on, mate. Do your thing. There we go. So we've combined our three different plots. We have our scatter plot, we have our distributions, and identity plots on the x and the y-axis. So we can see that there's a whole lot of crossover between the relationship between these two variables across the observed and the synthetic data sets. So this confirms that the relationship between these two variables is extremely similar between the two data sets. It's a very, very nice visualization. I'm going to go back and do a manuscript and see if I think I'm going to go back to my messy script and person condition self-report spirituality. I think this is the one. That is here. Copy and paste. Yeah, this is going to do a direct comparison for oxytocin condition by spirituality. OT. Yeah, typo. That'll do it. Cool. Error. Just going to try again from scratch. Documentation. Multi-compare. Gone too far. Object. Sins, yeah, data. Let's flip this around. Maybe that's the problem. Nope. I have no idea. I'll have to return that one. So, no clue. Ah, I do remember for some reason I had to reset as a data frame, and it worked last time, and I have no idea why. But let's just do it again. I did that too. Condition first. Spirituality. I don't know why this worked last time, but it just did. Fingers crossed. Yeah, of course it works. There we go. Why was this interesting again? I don't even remember. So we have... Okay, so for all the levels of... Yeah, okay. That's cool. So we have, it was a Likert scale from 0 to 7 for how much spirituality, self-reported spirituality that you felt, or how spiritual you felt. This shows you the count for each level within the Likert scale, running from 7 of no spirituality to 0 to no spirituality, 7 to a lot of spirituality. There was no A's, I think, and it just demonstrates that for each condition. Yeah, okay. This is interesting. Cool. Okay. So that worked for some reason after you've made it into a data frame, even though it already was a data frame. Let's just double check that. Is data frame OT dat. Yeah, it's so weird. It already is a data frame. Yeah, I don't know. Strange. Now we have this object, and we're going to call it fig 1b object. Yep, going to do that. Then we're going to extract the plot. I'm not sure what it's going to be called, but I'm going to find out. Fig. How have I structured it? 1b. Got to change the other one to 1c before I forget. 1c. Yep. Save. It's good. Problem solving on the fly. 1b. Fancy arrow. Here. Gonna check how the old stream's going. doing its thing. Yeah. Okay. This extract the plot. It's probably going to be called plot. Let's find out. Ooh. Maybe not. Oh, that's annoying. Oh, you're kidding me. Nope. Oh. Multi-compare. Come on. Oh, that might do it already. Let's just try create a thing. See if that works. Come on. If it doesn't, I don't know what I'm going to do. Something's happening. Go, you good thing. Come on. What do you got for? Yeah, ugly as sin, but I can work with that. I can totally work with that. I think. All right. Obviously, I have to tweak the dimensions, but yeah. Cool. A lot of potential. A lot of potential. Looking a little ugly, but we can see there's a bit of potential there. There we go. So that's Fig 1B. We'll rename that Fig 1B. Yeah. Sweet. Just call it Fig 1B. There we go. Rerun it. For multi. Spell check. Multi. Compare. Yep. Okay, that's 1B. And now we have 1C. See if this works. It's thinking. It's doing something. Let's try again. There we go. Now I want to check out the documentation. Okay, first let's go back to what I've actually written in the manuscript. So we're going to do the main comparison of the four variables in 1A, bivariate comparison, which we just plotted in 1B, and the relationship in 1C. 1D. I've skipped one. 1C. 1D. All right. Back to our plot. Sorry, back to our code. Here. Save it. Back to our messy script. Down here. Okay. This is an important step. Also revealed no replicated unique sets of values in the synthetic dataset. This was a very small line. Let's find it again. RU, I think it was called. Yep. Replicated uniques is the one. Units. None. False, false, false. Yep, that is good. Next step. Alright, the Ttest. So I'll just quickly go back here, talk about cowplot. One of the functions in cowplot is plotting grids, and here basically specified that we're going to be combining figure 1a, figure 1b. We're going to give them labels of A and B, and it's going to be within one column. And so you can specify how many you want in a column, how many you want in a row, and you can even adjust the label size of how big A and B is as well. So this is, we're going to call it fig 1. Nope, fig 1, yep. Fig 1b. Really? Yeah, that's why. Okay, we'll try again. Remember, this is going to probably look pretty ugly. Going to go back and fix it up in the future. You make something. Sometimes it will just think and do nothing, which I think is what's happened here. Try again. I'm going to go back up to fig 1b. There. So it's created the plot. We'll go back here. To create our temporary ugly plot, which we're going to fix up later. Come on. There we go. Okay. Yeah, so A and B, look, that size 12 is pretty good. Maybe we can go back and fix it up a bit, but I reckon that's alright. Yeah, alright, replicate uniques. Alright, so we're going to go back and look at this Ttest. This is my code. Why did this work? We'll never know. Alright, Ttest. This seems to be correct. Yep. So what we're doing here is we are testing the specific utility of a Ttest, which is the comparison of self-reported spirituality between people who are given intranasal oxytocin and placebo. Were there any significant differences in self-reported spirituality between these two conditions? So you can traditionally just run a Ttest. Let us go and get the correct. So I'm just going to paste this for easy access into a Word doc, a text file, so I can easily copy and paste. Probably a quick way to do that. That is what I know now. spirituality here. There. Just run this. Yeah, so this is our Ttest. One thing I've noticed, why have I done that? Is this still going to work? Could be a bit confusing, but let's just try that. Seems to have worked, yeah. Okay, so what I'm doing is I am running just a normal Ttest, which is Welch's Ttest, because I'm assuming that the variances are not equal, and Welch's Ttest is a good alternative, or is what you do, or one test that you do if the variances are not assumed to be equal. So there's your Ttest here, and what I'm doing is I'm running a linear model equivalent of the Ttest, which is here, which gives us the same outcome. So we have 0.26, 0.26, 1.13, and 1.13, but it's reversed, but it's still the same outcome. So there we go. And we can also get the confidence intervals here as well. Okay, so the next thing we're doing is okay. This is original, generalized linear model, or maybe LM and SLM. Here. Yeah, this is the same thing, I believe. So what we've done, let's go back to our Word document. So this is reporting the Ttest and the equivalent linear model. And now what we're doing is creating, fitting a linear model from the synthetic data here. And here, data OTSIM. Now what we're doing is we are comparing the performance of the synthetic linear model against the equivalent linear model in the original dataset. Doing it with this command here. Bingo, bango. That is good. Yeah, okay. So what we've done here is we are comparing the synthetic and linear models, and we can see these are almost exactly the same. So although the synthetic data, this represents people that don't exist. These are new people that don't really exist. in reality, running the same t-test, which compares oxytocin and placebo, yields almost exactly the same result. So you can see here the synthetic and the observed, and if you look at the overlap, there is 99.9% overlap in the confidence intervals. You don't need a statistical test to tell you that those are absolutely equivalent. So there's a super equivalent there. This is good, and we've written this up. Yeah. So this suggests the method used retained all the relationships between the variables that influence the parameters of the fit, the model fitting parameters. Very better. Next thing that we're doing. Yeah. So we're reporting the fit for the overall model, which is reported down here, and next we're reporting the differences in the coefficient, which is here. Okay, and then we are showing figure 1D, which is here. Now we're going to extract figure 1D. I call this Ttest.com. There. If we run that, we're going to extract. Let's figure 1D here. Extract this. Plot. Please be a plot. Plot. I think that is it. Let's find out. Figure 1D. Yes, there we go. There we go. I got an A. Okay, cool. Now, let's combine them all together. First, let's just create an ugly plot just to make sure that it all works. And then let's see if we can work out the dimensions. Figure 1 there. There we go. Okay, I'll adjust that. C, D. What I might need to do is to combine a few plots. But let's just see how ugly this looks first and what sort of dimensions we're working with. We're doing two columns. See how that works. There we go. I hear my daughter's awake. She wants to come in. She loves computers. But Mum's with her today. Okay, let's do figure 1. This might take a while to knit together. Still going. So what you can do is you can actually do 2 plot grids together. Sometimes that's just easier when it comes to figuring out the dimensions. So I know that figure A needs to be wide. I think figure B also needs to be wide, whereas C and D can be small. So what I might do is I'll create 2 different plot grids and then combine them together. So we're going to call this Fig 1 plot grid 1. And then we're going to say that. That. Number of columns, 1. I'm going to do plot grid 2. That plot still isn't knitted yet. Figure 1C and D, and call this C and D, and we want 2 columns for this one. How's this one going? Still doing its thing. It's freaking out. You think you have a good computer until it comes to actually pasting together a few figures, and the whole thing, the fans just go crazy. Okay, there we go. Obviously, it's a bit messy. So what I'm going to do is I'm not as bad as I thought. So I'm going to put that. How am I going to do that? So C and D are almost too big. B is perfect. And A looks like a mess. A needs to be much wider. So what it can do is put A on its own and then add B, C, D. Making B small might be too small. Let's give that a go. Alright. Plot grid 1 just has 1. Grid 2 has figure 1B. And then we call it B. What's going on? Yep. BCD. Number of columns, 3. So let's make that. Will it make it for me if there's just 1? Probably. Let's find out. Something's happening. Okay, yeah, there we go. 8. And then plot grid 2. Let's make that 3 columns. While it's doing that, let's make our master plot. One, 2. We're not adding labels because we've already added labels, and we are having 2 rows. Okay, see how that works. Label size is redundant. Come on. Putting 3 together should work. Yeah. Yeah. Well, super ugly. Bit better. Ah, gee, I wish this was at an angle. It's okay. Alright, see how that goes. BCD, and we're going to combine this into master line. Oh man, plot grid, amazing. Super, super easy. See what this looks like. This can be very tricky to put together, but there are ways that you can adjust the relative dimensions. Oh man, it's that bloody thing there. Alright, that's going to need a bit more tweaking. But the general... That's better, but the top one's too wide. Okay, what I can do is I can adjust how the top one is presented. Rather than doing 2 rows, I can do that could work. That could work. Might be too squashed. Let's try that. Let's go back in the documentation. Compare. And col. And col equals 4. Yeah. There. See how it looks. It's better, but age still squashed. That's annoying. Why not just make it vertical? Is there a way of doing that? Probably not. What does this do? No idea. 10. What has it even done? Ah, that's better. Yeah. Cool. So we can see the synthesis method. The only thing that's really stood out is this one age thing. So there's a bucket here. Where the real count is 5, but the synthesized is 7. That may give us some differences, but let's adjust it a bit more. So I do 12. Sometimes you just need to play around with stuff. So 14. So 16. Alright. So yeah, I'm happy with that. Let's do that. That was dead end. Create that within cowplot, plot grid. That should be the same. Don't know why we ran that. We'll wait for that. And do figure 1. Doing its thing. Something's happening. Hopefully this looks a little bit better. But at least I know how to adjust those histogram plots from the compare function. try again. That is looking pretty good. Not super happy. Okay. Progress. 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 Not awesome, but it's still pretty good. Cool. All right. I'm going to wrap up for this streaming session. Make sure you check out the old videos on my YouTube channel if you are interested. Thanks for dropping by.